Yeah, am I audible?
Yes, sir.
Okay, are you able to see the screen?
Yes, sir.
Okay, thank you. Yeah, very good morning. I hope I'm audible, and I think the screen is also visible. Okay, so this the last lecture we have defined a new concept called random variable for a certain means which will be associated with a random experiment and which constitute a sample space omega. Okay, and we have defined a random variable. Okay, right. So what we have learned is that the random variable is a real valued function. Okay, and we have also learned that it will not be, you can, I mean, there is no uniqueness regarding the random variable. Okay, and also we define the associated probabilities to it. Okay, which we name as probability mass function. Okay, right, and okay, fine. So we have defined uh, discrete random variable as well as continuous random variable. And so it is most of the, it is very easy to identify that when you will say a random variable is discrete or when you will say it is continuous. So if you are able to find out that this that range of this the sample space that random variable is finite or countably infinite. Okay, or in other words, X assumes discrete values instead of continuous values. Okay, then we say that random variable is discrete. Okay, and we have identified its EMF, which we denoted by this px, where the suffix x denotes the dependence. Okay, just simply mean. Okay, right. So which is defined as the probability for at values x equals to x. Okay, and it certainly has some attached properties, that non-negativity and normality condition, you can say. Okay, means if you sum up all the values of this over the whole sample space, or for all values of x, if you sum up, that will lead to 1, and all of them are non-negative. Okay, we have seen that. And I hope now onwards you are also comfortable with this notation, that x equals to x means the set of all possible outcomes in omega, such that x assumes value x, okay, for that particular event omega. Okay, right. So I hope you all are comfortable with this now. Okay, and so this is called non-negativity condition, that for each value of x, this EMF is non-negative. And the second is the known as the normality condition, where if you take sum over all the values of x, and if you sum up all these probabilities, that will lead to 1. And we have also made a statement that if you are able to find a function which is such that which satisfies these two properties, okay, so it will be, it means you can, means there will exist a random variable for which it becomes a PML. Okay, at least existence is there. We don't know which random experiment is performed and what type of random, I mean discrete random variable we know, but previous story we don't know, but there exists a random variable like that also, that can be guaranteed. Okay, right. Now what was the next was is we also identified this cumulative distribution function for discrete random variable and or continuous. This is the definition. Okay, and when it case the continuous, this if you followed the earlier discussion carefully, that's nothing but the summation of all the properties, all the probabilities, okay, for each value of x such that x is less than equals to a. You sum up all this is going to give you the CDF of, or in short, I mean this is a short form of cumulative distribution function. Okay, right. So this all story we know. Okay. Okay. We also identifies that in case of discrete random variable, CDF will behave like a step function. Okay. And it's a non-decreasing, those all properties we listed out there. Some of the properties we have listed out there. Okay. Now we have also given the definition of continuous random variable. Okay, so we say that a random variable x is continuous if you are able to identify a function which is having this property that it is non-negative. Okay, such that it is this is a definition of associated probability, but with this non-negativity condition, it has another definition also attached with it, is minus infinity to infinity fx of x dx is 1. Okay, over whole real line, it covers the area, which total area is, you can say, 1. Okay, right. So for any subset of real number, you can define the probability in terms of integral, because the x can assume values in continuum manner rather than the discrete manner. And you know the summation will tends to the integration. Means you have, I hope you have seen such type of behavior when you have talked about the Riemann integral. Okay, right? Okay, so this is the way of assigning the probabilities for continuous random variable over the subset of R. Okay. So here it is. We have this is the definition, that non-negativity and normality condition. Okay, and if you look at the right side, what it tells you is this gives you the how this area, right, fx of x dx, what it will denote. If you go back and check, okay, in the Riemann integral, this is nothing but fx of x is nothing but the height, and dx is the length of that partition interval. So it denotes some area of that rectangle, possible rectangle. Okay, which can be looked at like the probability. Okay, this probability where x assumes a value between x to this length interval x plus dx, which has the length. Okay, and if you sum up all this, means integration minus infinity fx of x dx is equals to 1. Okay, so this approximation will help you later in your research. Okay, right. Okay, now we have so for the continuous random variable, so far it is fine, right? This is the definition we have already looked at. Okay, and if you really care about this, what is the x less than equals to x means is nothing but the x, like it means x can take any values x or less than. That means minus infinity to x close interval. And if you follow the definition, integration will take this place, minus infinity to x f of x dx. I don't think so any issue is there to follow the definition. Okay. Okay. Now, the very first thing which we have not seen, I think we have not seen in the last session. Okay, that these properties. Okay, the first property is that fx at the left hand point of the real line. Okay, left hand point of the real line is minus infinity. And you know, x less than equals to minus infinity. So it is an impossible event. Okay, it is an impossible event. X is always strictly greater than minus infinity. You know, it cannot take minus infinity or plus infinity. Okay, so this is going to be impossible event, and this is going to be 0. Now, fx at infinity, the right hand point. So it is a union of x less than infinity, union of x equals to infinity. Okay, means it will take all the values of possible x values. So whether you talk about the case of discrete or continuous, in both the cases, it will lead to 1. You can assume x equals to infinity is an impossible event. Okay, and you can use the fact that probability function is, you know, follows the countably infinite additivity property. So it's going to be probability of x less than infinity union probability of plus probability of x equals to infinity. X equal to infinity is a impossible event. Okay, and x 60 less than infinity will lead to the value is 1. Okay, the third property, fx is non-decreasing, that we have seen, and that immediately follows by looking at this. So if you take x1 60 less than x2, any two real number which are related with this, so certainly you have the following. X means if you look, draw the graph. Okay, if you draw the graph, it is easy to follow that this set x less than equals to x1 is going to be a subset of x less than equals to x2. And since probability is a monotonically non-decreasing function, so probability of x less than equals to x1 is less than equals to probability of x less than equals to x2. So it follows this. Okay, it's non-decreasing. Similarly, you can also establish the following fact, okay, by looking at the properties. Fx is right continuous. Okay, so try to check it out. Okay, that you can look at as an exercise. That's also will be interesting problem. Okay, if you are very clear about your calculus, you can do it. Okay, and I hope you know what is the meaning of right continuity and left continuity. Okay, right. Now, so now see, whenever you are talking about a you can say a real life scenario, it is means it is always preferably go for more than one variable. Okay, so therefore there is always a chance when you are going to model some experiment, you may need to introduce more than one random variable. Okay, so there are various ways. So let's focus this example and then try to understand. Okay, and then means like if you introduce more than one variable, so definitely you need to have joint distribution now. Then how their probabilities will be defined, and so on. Those concepts are necessary. Okay, so let's start with an example, and then we will define the jointly distributed random variable. Also, before starting, I may also mention you that we are going to talk about, means if you are talking about jointly distributed random variable, either, so we are going to talk about only with respect to two. If you take two random variable, how will you define that their joint distribution? Also, means that can be extended to any finitely many. Okay, so to avoid the complexity here, so I am not going to touch more than two random variables. Okay, later on you can deal with it in your research or whenever you deal with a new project. Okay, however, we are also only focusing on the variables where both of them are either discrete, means both of them together will be either discrete or continuous. We are not talking about mixed. Okay, here at least. Okay, means you have x random variable and y random variable. X is discrete and y is continuous. How will you identify their joint distribution? We are not going to address that issue here. Okay, both of them are discrete, both of them are continuous. So in that case, we are going to talk about right. Okay, right. So let's take this example. Okay, let's take this example. Suppose that three batteries are chosen from a group of three new, four used but still working. You have these information. Three new batteries are there, four used battery but they are still working in condition, and five defective batteries are there. Okay, now let X denotes the number of new batteries that are chosen. So three batteries are chosen out of this stock. Okay, so I have identified a variable X such that number of new batteries that are chosen. Okay, and Y denotes the number of used batteries that are chosen. Okay, now it's so number of new batteries that are chosen, or Y number of used batteries that are chosen. So first of all, you need to know what is the value, means the X and Y, what values they can take. So if you focus on X, number of new batteries that are chosen. So you have chosen three batteries, so that's known. Okay, and you know maximum three new batteries are there, maximum number is four used batteries are there, and maximum is five defective batteries are there. You can also identify Z as a number of defective batteries that are chosen. That also you can do, but I'm restricted only with these two. Okay, so now X denotes the number of new batteries that are chosen, means what are the values X can take. Either none of the new battery chosen is zero, one new battery and other either used or defective, two new batteries, okay, and other one either from used but still working, or five or from a defective battery set, and all of them are used. Similarly, you can also talk about the range of Y, that it is can be taken either 0, 1, 2, and 3. Okay, now we wish to define the relationship between these two random variable x and y. Okay, so there are now two random variables. So some experiment is performed. What is that experiment? Is 3 batteries are chosen from a group. Okay, you can say from a bag which contains 3 new, 4 used but still working, and 5 defective batteries. Okay, so that experiment has been occurred. So associated, you have 2 random variables. Now you want to know how will you identify the relationship between them. First of all, by looking at their range, it is very clear that both of are assuming the discrete values, so they are going to fall into the discrete random variables case. You can also individually talk about. You can also identify their individual probability. Associated PMF also you can talk about. Okay, you can also talk about their associated PMF in each case. I think that you can find out. Okay, you can find out Px of x and Py of y. That's very easy by using combination or permutation combination rules. But how will you identify both together jointly? How will they work? So first we will try to identify the joint CDF. Okay, so joint CDF. For looking at the joint CDF, you know. Okay, let's go with that. So you have, this is, you know, these are CDF for the random variable x and y respectively. I hope you follow the definition. Now, their jointly happens means you will have and. Okay, it is important to understand. It will come here and. Okay, so what it tells you is means you are, so now this f, if you look at this f with suffix with x comma y, means it is jointly depending on both x and y. Okay, so by looking at the this CDF for x and CDF of y, so what is the how will you generalize this to this, right? Probability of set of all possible events x less than equals to x and set of all possible events such that y less than equals to 1. Okay, it can be generalized. Okay, you are able to see these arrows also. Okay, so generalization means you can go back. Okay, generalization means you should go back, means from this joint joint CDF, you can always able to identify. These are also known as marginal CDFs. Okay, so they are marginal CDF individual also. How? Okay, now if you know, see, if I able to draw, means like, see, x is a random variable, okay, and y is also a random variable. Okay, now you take the case this x less than equals to x. Okay, I am taking this intersection with because with the sample space omega. Right? I'm again going to use the same concept which we have used in case of total probability case and Bayes theorem also similarly. Okay, so it is equal to, I'm going to write x less than this set is equals to x less than equals to x. I'm writing this intersection of omega. I'm writing at union over j. You have this is going to be y less than equals to yj. Can I write this? Wait a minute. No. Yeah, it will form, right? If you take all the possible yj's, it is going to be this. Right. Now this I can identify as union of j x less than equals to x intersection with y less than equals to, I may say this by j, right? Yeah. But now, can I use the the case that this countable infinite additivity here? Yes? Can anyone tell?
Sir, can you please repeat the question?
I'm asking you, I'm to apply here probability. Now, I'm going to apply this probability on the both side function. Can I write it as summation over j and this probability of x less than equals to x intersection with y less than equals to yj, or and?
No, sir. No, sir. Because these are not mutually. These are not disjoint events. That's why.
Yeah, so I can't write this. So what we can do?
Sir, we can subtract out the, means you can use the principle of inclusion and exclusion to find out the probability.
I didn't get you.
Sir, we can use the principle of inclusion and exclusion to find out the union in terms of the disjoint sets, and then find the summation of that set.
Okay. So instead of that, but now my question is, I wish to go back from here to here. Okay. How will you proceed? This is the way. Can I write it in the joint? Means I want to relate this fx of x in some way to fx of y of x comma y.
Find fx of fxy of xy for all values of y and one particular value of x.
Then
in that way we can we find fx of x?
see now see, can I means wait a minute, I'm just going to again rewrite this all the things now again. Let me have this. This is there. Okay. Now I'm going to write in the same. What I want is this is going to be. This is I want this is to be somewhere related with the fx of x. Right? Means this is what is fx of x. Okay. Now, yeah.
Sir, we can write the event x less than equal to small x as the intersection of it with omega, and we can write omega as the union of events y less than equal to y and y more than y, and that way the events x less than equal to x intersection y less than y, and the event x less than equal to small x intersection of the random variable y more than equal to y. These will be disjoint events, and we can write them as the summation of the events.
I didn't get you. Did anyone can explain his? Somewhere I have lost the flow.
Sir, what I was trying to say is we can write the event of random variable x less than equal to small x as the random variable x less than equal to small x intersection omega, and we can write omega as the union of the events y less than equal to small the random variable y less than equal to small y, and the random variable y less than more than equal to more than small y.
So can I write omega as y less than infinity?
Yes, sir.
So whether
Yes,
it is
sir.
continuous or
Yes, sir.
discrete, right? So now in the previous notation, what it is? This is fx comma y with x comma infinity. Is
Yes,
that
sir.
fine?
Yes, sir.
Of course, see, infinity means, see, if you include here equal to sign, you will say impossible event, that you can write as individual and use the probability definition, and that's an impossible event, that's a zero probability. Okay, so similarly I may write, so we will see more clear picture when we will write joint PMF and joint PDF. Okay, now this similarly I can write this Fy of y as which is probability of you can say y less than equals to y. Now instead of running the values over y, now you can run the values over x, you can say. Okay, so that's going to be probability of or instead of that I will write straightforward fx of y comma infinity comma. Okay, you fix the values x and summing over infinity in roughly I'm telling. Okay, I hope this convinces you. Is that convincing?
Yes, sir.
Fine. Okay. Now we have written this. Okay, fine. So I think I don't want to go with this. Okay. So we define the joint CDF of x and y as follows. So we have already defined this. Okay, right. Now one can obtain the individual CDF of x and y as follows. That's we have just now made clear. Okay, right. Okay. Now let's try to understand. Now in the similar fashion, we can also define the joint PMF. So if both are discrete case. Okay. So we want to associate probabilities jointly. Okay. At each values xi and yj. So xi and so we don't means we are differing with I and j. So xi is the values related with x and yj are the values taken means related with y random variable. So jointly you have a PMF as px comma y, xi comma y. This is notation. Okay. So this can be assigned the probability of x equals to xi and and y equals to yj. Both will happen together. Then that will be assigned as the joint probability. Okay. We will try to get back to our example and then we will try to more relate. And individual probabilities are we are already well known about it, right? So these probabilities you are already well known about it. These are PMF of y and x respectively. Okay. Now again you can get back to this, right? You can get back to this by using this results. Okay. So I hope in the next slide I have written that. Yeah. So here it is now, this is x equals to s. If you are this x equals to xi, you can write as union of j, x equals to xi and y equals to yj. Just followed the previous discussion. Okay. Now these are, so now these are the, see, y equals to yj, each is individual. So over summing up over this, these are individual probabilities and they are disjoint. Okay, so you have this summation over j, it's easy to follow. Okay, the countable infinite activity will work here. There was the challenge that you are having the less than equal to. Okay, so that is why there was a challenge. You cannot write directly their summation. Okay, because it will cover all the previous values as well. Okay, so this is, so if you summing up over j means, or with respect to the y variable, you will get the marginal PMF of x. If you're summing up over the x variable with respect to x variable, first variable, you are going to get the marginal PMF of with respect to y random variable. Okay, right. So this discussion is over. So now let's go back and have a discussion over here. Okay, let's see how will we identify now joint PMF of x and y now. Okay, now here x can assume the values, x can be taken any value from 0, 1 to 3, and y can be taken from this set 0, 1, 2, and I'm looking for the joint PMF, okay, at different values. Okay, now let's look at the first, let's look at this 0, comma, so x is 0 and 0, comma 0. This all the possible pairs you can make, and I'm going to discuss one by one up to some extent. Okay, so this is definition is probability of x equals to 0. You also try it, okay, with your pen and paper. So x equals to 0 and y equals to 0. What does it mean? So x denotes the random variable, that number of new batteries that are chosen. So x is 0 means none of the new batteries chosen. Okay, y is denotes the number of used batteries that are chosen. Y denotes 0 means none of the used batteries are also chosen. So only coming from defective batteries set. Okay, and what is the experiment is 3 batteries are chosen. So out of 5, all 3 are defective batteries now. Okay, 5C3, right? So total favorable outcomes are 5C3. Divide by, so total is you have 5 plus 4 plus 9 plus 3. So total possible exhaustive cases 12C3. Okay, now 5C3 you solve it out. Okay, so this is going to be 10, right? 5C3 is 10, and 12C3 is 12 into 11 into 10 divided by 6. You have, this is going to be 10 divided by 220. Because see, I'm going to fix it 220 because it will coming up again and again. I'm not simplifying it. Now, if you look at the next, let me say px comma y of 0, comma 1. So definition is probability x equals to 0 and y equals to 1. Now, so total number of possible exhaustive cases are 12C3. Now, no new batteries. Okay, so number of new batteries. So from here, none of them is coming. One of the batteries coming from used, and rest of them are from defective. Right? So 4C1 into 5C2. 4C1 into 5C2. So that's going to be 10 into 4 is 40 divided by 220. This is the probability of this. Right. Now, let me have another one. So px comma y of 0, comma 2. X equals to 0. Y equals to 2. So now none of the new battery, 2 are coming from the used battery, so 4 out of 2, and one of them is from the defective one, 5C1 divided by 12C3. So you have 4C2 is 6 into 5, 30, right? 30 divided by 220. Now, Px comma y of 0 comma 3. That's going to be probability of x equals to 0, y equals to 3 is equals to, so all of them are coming from the used battery cases. So you have 4C3 divided by 12C3. So that's going to be 4 divided by 220. Now, another pair possible is x comma y. So with 1 comma, so 1 comma 0. If I look at 1 comma 0 is probability of x equals to 1 and y equals to 0. So now I hope it is easy to follow. So new battery 1 is coming. So out of 3 new, 1 is coming. None of them is coming from the used. Rest of them are coming from the defective. So 5 choose 2 divide by you have 12C3. So this is going to be right 10, right? 10 into 3 is 30 divided by 220. Px comma y of 1 comma 1. Probability of x equals to 1 and y equals to 1. So out of 3, 1 is coming, right? New battery. Out of used battery, 1 is coming. And the rest will come from the defective. So 5 choose 1 divided by 12 choose 3. So that's going to be 60 by 220. Right? Now, if I may complete this, let's complete this row. X comma y of 1 comma 2. That's going to be probability of x equals to 1, y equals to 2. So out of new, 1 is coming. Out of used, 2 are coming. So there is no defective battery. So 12 choose 3. So that's going to be 6 into 3 is 18 divided by 220. Now, if I look at this 1 comma 3, so this is also possible pairs. X equals to 1, y equals to 3. It is an impossible event because this will give you 4 battery, but 4 battery is not the case. It's impossible event. So this probability is 0. Okay, this probability is 0 because this is an impossible event because the random experiment is of 3 batteries are chosen. Okay, and so on. So similarly, you can go with the 2 comma 2 and so on. Okay, right. So now let's come to the table now that I have written down here. Yeah. So this is the table. You can match your values. Just now we have written down. Okay. So you have okay. So you have this. These values are the values paired. Okay, at other pairs. Okay, 0 comma 0. So this column is for x values. This row is for y values. Y equals to 0, y equals to 1, y 2, y equals to 3. This is for x equals to 0, x equals to 1, x equals to 2, x equals to 3. Now, if you are interested in probability at x equals to 0, you sum up this with respect to all values of y. That will lead to the 84 by 220 that you can verify. If you go back and check probability of x equals to 0, okay, none of them is new battery. So they are coming from either from the used battery, favorable cases, right, out of used battery or defective battery. So out of I think 4 plus 5, 9. 9C3 divided by 12C3. Right? Is that 84? What is 9C3? So you have 9 into 8 into 7 divided by 6. Right? Just a minute. Wait a minute. This is 36.
It would be 9 into 8 into 7.
Sorry, 7. Yes, yes, 3. Yeah, okay, okay. Yes. You have 3, 2, this is 4. Yeah, this is 84 by 220. Yes. Okay. Right. So it is coming. Okay. Similarly, you can also verify for x equals to 1. Okay. One of the new battery. Okay. Other is defective or new use battery. So that means like you have out of 3 new batteries, 1 is coming, and there are 9 choose 2 divided by 12 choose 3. We can verify that's going to be 108 by 226. And this sum also, these 3 sum, this also lead to 108. So you are summing with respect to the y values. That will give to the probability at x equals to 0, x equals to here 1 case. Similarly for x equals to 2, similarly for x equals to 3. Okay. In a similar manner, you can also find from this table, if you define this if you got this matrix here, okay, you can also find out by some of the you can say first column elements that will lead to the probability of y equals to 0, then the next y equal to 1, y equals to 2, y equals to 2. And also you can verify now if you sum up all these 4 values, probability x equals to 0, x equals to 1, x equals to 2, x equals to 3, that will lead to the 1. Similarly, if you sum up all these values, 4 values, that also going to be 1. So they are also identifies. Okay, right. Now let's take one another example. Okay, and I want you people to try to get some try to find the joint distribution for some of the values. Okay, right. So let's read this. Suppose that you have suppose that 15% of the families in a certain community have no children. 20% have 1 children, 35% have 2 children, and 30% have 3 children. So total, if you sum up is 30, 35, 20, 15, that will be in total is 100. Okay, so 15% of the families in a certain community have no children, 20% have 1 children, 35% have 2 children, and 30% have 3 children. And also it is given that each child is equally likely to be a boy or a girl. So if you distinguish boy or girl, it's with probability 1 by 2, equally likely. Okay, either a boy or a girl with probability 1 by 2. Okay, right. Now, if a family is chosen at random from this community, you can say for certain award or some whatever, best family, whatever you call. So if a family is chosen at random from this community, okay, B, the number of boys denotes, G denotes the number of girls in this family. Okay, write their joint PMF. Okay, so a family is chosen, so any family can be chosen. Then B denotes the number of boy and G denotes the number of girls in that particular family. Write their joint PMF. Okay, so certainly you know, right, how many number of boys at most is 3, either none or 3, because there are families with 3 children. Similarly, girls are also can take place up to 3. All are equally likely. Okay, so B and G denotes the number of boys and G denotes the number of girls. They both can take values from this 0, 1 to 3 set. Okay, now try to identify their joint PM. Okay, so Okay, so if you denote this joint PMF by P and this is B comma G, you have to verify, you have to find the values of B equals to 0, G equals to 0. Okay, so you have to find this. So comma G with 0 comma 0, first pair. So probability of B equals to 0, G equals to 0. What is that?
15%? 50%?
15% means 0.15. Means this is equals to the probability of it, what is this equals to? How do you read this? This is nothing but the event that the family is chosen from no children.
Yes.
So no children family. I'm just writing or family with no children. So that's so that's a 0.1. Good. Okay. Now try to answer this now. 0 comma 1. Probability of B equals to 0 and G equals to 1.
0.1.
0.1.
How?
First,
1 by 2 into...
It is, I must write here is, it's going to be probability, okay, that family with, I should write is family with 1 children into anything.
1 by 2.
probability that it is girl given
1 by 2, because it could be either a boy or a girl with probability, okay, probability of the child is a girl or girl child, whatever you want to write. So this is going to be probably with 1 children is 20%, right? So that's 0.2 into probability of child is a girl, that's a 1 by 2. So that's going to be 0.20. Now let's have this probability of B comma G with 0 comma 2 means probability of B equals to 0, G equals to 2.
$35 by 400.
How will you read this? So you have this is surely with family with 2 children, that's a 35%. Okay, so the certainly is going to be probability of family with 2 children into. Is there any into?
1 by
Into
4.
probability that both the children are girls.
Both the children
Into
are
by-
girls.
both the children are girls.
Yeah, both the children are equal, that's equals to 2. Yeah, both the children are equal, but out that probability that both of them are girls.
1 by 4.
1 by 4.
Yeah, 1 by 4. That's it.
No, sir. I think
Okay.
1 by 3
How?
because boy girl or girl boy वो दोनों सेम ही होंगे ना means.
Yeah, they are same only. So total is 2. So how many possible pairs of girl means 2? So right, girl is 2, right? There are how many pairs are possible, right? BG, right? 2 families, right? BG, GB, BB, and GG. So what is the favorable one? GG, right? And out of 4 possible. So 1 is favorable out of 4 possible. Is that make you clear?
But sir, BG and GB are
GB
equivalent,
same,
right?
हाँ
Huh?
BG और GB सेम ही
But
रहेगा
they
ना
are not
एक ही
favorable, no?
case.
No, but they are not favorable us. See, order doesn't matter, but they are there, right? They are same. That's true. But here we see what are the possible. See, if you have when you are writing very specifically B equals to 0 and G equals to, what are the possible with this? So B, G, 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 V, V, G, V. That also possible. So there are total possible is 4 possible.
Means sir, when we are going for E of BG 1 then we take 2 by 4, right?
One. Yes. You have to. Wait a minute. So 1, right? Yes, you have to.
Sir, we are defining families by their number of children, right?
Yeah.
So it is only 0, 1 or 2 or 3, sorry. 0, 1, 2 and 3. So there when we define that there are 2 children, so it would be like 0 boy, 1 boy or 2 boy.
0.
Similarly, 0 girl, 1 girl or 2 girl for a family with 2 children. So then there can be only 3 cases. Now BG and GB are not considered in the case with 2 children. I mean like to say that.
Yes,
See,
sir. Why will
when
the
you are
cases
going
of
to see, they are equally likely though. Okay, but the thing is, when you are looking in particular, okay, how many number of possible outcomes? So total family is 2. Okay, if you are going with suppose 1 month. Okay, so see, we are not in particular case that first is boy and second is girl, or second is boy and or first is girl or second is boy. But see, what are the possible pair? Because we are looking in this regard, right? B and G. We are defining them in certain order. First pair is for D, and second pair for second variable here stands for G. Okay. Now you are trying to say why we are not taking this BG and GB are equal, A or a single case. So then in that case, see if I then I think see when you are identifying, when you are going in particular with the child, okay, so then being a girl or a boy, okay, with the probability is 1 by 2. Okay, that you have to keep in mind. So 2 child family, and if you have certainly 2 is there, okay, I don't find, if you are having, because you have 2 places, okay, here is 2 places, okay, for a family with 2 child. Okay, now one is being girl, first is being girl, and second is being boy. Or so there is an age difference. So this is how you can also order them. Okay, so they are not going to be the both of them at the same age or something. Does that make sense?
sir, but why will this order matter over here?
See, when order is not important, okay, in that case, just a second. Let's
Hello, sir.
yes.
Sir, I think order doesn't matter when in case of twin childrens when both are twins, but when
Say if you are
both are not twins, then order matters. So if we consider the case of twins, then probability will be 1/3 for all. And if we are not considering the case of twins, then order probability will be 1/4, 1/4, and 2/4.
Sir, but we are not considering whether the boy is older or the girl is older over here.
No, see, boys is older and girls is older, but they are two different, right? They can say one of the pairs. So see, you have to identify all the possible pairs. Okay, like see, this is not. It is a kind of ordered pairs. You can say means ordered set. Okay, so you have the set where you can say these are the possible. See, I'm writing in this fashion. You may write in B comma G, G comma G. Both are B comma B or G comma B. So that can be distinguished in terms of their age. Okay, right? Okay, so see when I think. Okay, and see, I think
then maybe in the question it should be written there are no twins or something like that.
it is, see, when so when nothing is there, so then you have to use random, right?
So,
Is-
sir, we will have to consider the probability of twin children and probability of not twin children into consideration.
See, each child is having some number. Okay, so you can see if you have, this is right. I am just right. This I can name at like B0, B1, B2, B3, and G0, G1, G2, G3. It also can be random. Okay, somewhere like, okay, and wait a minute, where I am going. Okay, yeah. Okay, so see, family with two children. Okay, let us come to the new. So you have a family which has two children. So there are families F0, F1, F2, and F3. These type of. So there are 0 children, 1 children, 2 children, 3 children. So you have 2 children family. So one could be boy, both could be girls. Means B and not in this way. So you are in this way. In this case, okay, 2 child. Okay, now then you have see there you are saying that you have both could be boys. You're not, see, both boys and both could be girls. Okay, first could be boy, second could be girl, first could be girl, second could be boy. These are the possible, see, four possible pairs. Okay, means you can differentiate them with respect to their age as well. Okay, but if you do so, then how will you? So first is, so then you will say that this B1 and B2 both are boys. They are also going to come like B2, B1 as well. So, right? Am I right here? if I go with your twin case or means like by age, okay, so B1 is elder and B2 is old, means younger, or B2 is younger and B1 is elder, so they all are possible outcomes. Okay, so we are not differentiating with respect to their age here. Okay, I don't think so. I'm not with that concept that twins will help you here for 3 cases and for that matter. If you are really only taking care or taking care of the taking care of this, so they have different names, right? You can say both are boys, but they have different names. Okay, so there are various parameters. Okay, if you introduce more parameters, it will make more complicated here. So, but all of them are equal. So each child will be treated as equally likely to be either a boy or a girl. Okay, so these are the 4 possible outcomes. Okay, which are possible way you can arrange them. Okay, is that clear?
Sir, in this sense, in a previous question, we should also consider order, like first 2 are new and second is.
If I get into this concept that older and younger, then B1, B2 and B2, B1 both are different cases. In my opinion.
But sir, the one which will have less age will be considered as B1, and
see,
the
you
older
have
one will
wait a minute. So I will just make it. I will try to, because I don't want to introduce here this binomial random variable. Okay, so you have 2 places. Okay, 2 children means 2 places. Each has 2 choices. This has also, because they are equally likely. Okay, this could be either boy or could be a girl, but that next one cannot be left. This also have 2 choices. So out of 2, the total will be 2 cross 2. That's going to be 4. So the possible when you have the first place as G and this is Z is going to be right. This is only one out of that. Right? So see, there are 2 childs. Okay, so 2 childs means this, if you box, this is the first child and the second child or whatever. This, there are 2. Obviously 2 things are there. So now this first child will be either a boy or a girl. Okay, with the probability you have, this is 1/2. So this will be this also you can look at in another way. This first child will be either a boy or a girl, will be with probability 1/2 into the second child also being a girl with probability 1/2. Okay, so that's going to be a 1/4. Okay, out of 2, choose 2. Okay, that will be possible outcomes. Okay, so that number of possible ordered pairs you can say is possible. So out of 2 children, both of them are is 2 choose 2, right? Is going to be the number of possible, you can say, ordered pairs. Yeah. Is that made clear now? Can I make it like this? See, girls are 2. Out of 2 children, girls are 2. So 2 choose 2. Both are should be chosen together. First girl with probability 1 by 2, second girl with probability 1 by 2. So 1 by 2 into 1 by 2, that is 1 by 4 into 1 is 1 by 2. Is that make clear? Rather going into this detail, because this will make complicate the problem. Now, I think now from here, this concept you can, so this is a somewhere related with the binomial random variable. Okay, that will may come later when we talk about the specific case of discrete random variables. Okay, now let's try to write down for let's say case this 1, 1 pair as well. Okay, let's take this case. This probability of B equals to 1 and G equals to 1. So again, probability that family with 2 child, obviously. Okay, that is probability with 2 children is I think I have 35%. So this is going to be 0.35 into probability that B equals to 1 and G equals to 1 given that family with 2 child in that case. Okay, now if you look at here, again, I've got this family with 2 child, you have 2 boxes. So 1 is boy and 1 is girl. Okay, now how many possible ways is possible? So first is boy, second is girl, or girl is first and second is boy. So, or in other words, in other words, I can have, this is going to be this is boy, this is girl. If you fix this, there are 2 possible ways. So 2 into, so probability of being a boy with probability is 1 by 2. Probability of being a girl with probability 1 by 2. So there are, so if instead of this, I may also write as 2 choose 1 into 1 by 2 into 1 by 2. So out of 2, 1 is boy. So with probability is 1 by 2 into the other one is the probability of being a girl. That's going to be 1 by 2. Okay, so this is going to be, I think now this is going to be 0.35 into this is going to be 2 by 4. That's going to be 1 by 2. Okay, is that make sense? Yes. Does that make sense now?
Yes, sir.
Okay. Now, similarly, you can talk about other things. So you can, I'm just giving you this table here and I will close. Okay. Try to verify. Okay. That these probabilities are, you try to verify that whether this final answers, I think these are correct only. Okay. I have matched already. So, but you try it yourself. These numbers are given to you. You can verify. You can find the joint PMF of boys and girls. Okay, right.
Hello, sir.
Yeah.
Hello, sir.
Yes.
Sir, can you show for 1 boy and 2 girl?
1 boy and 2 girl. Okay. Whether it is there? Yes, here. So probability of being a 1 boy and girl 2. Okay. So first thing is probability of 3 child family, that's with 30%. Okay. Now you have three child. So either you fix number of girls are 2. So possibly how many? 3 choose 2 into probability of being girl 1 by 2 into 1 by 2, that's 1 by 2 square, and probability of being means that last one is boy with probability 1 by 2.
Okay, sir. I got it. Thank you, sir.
Okay.
Yes, sir.
Yeah. Okay, thank you.